So welcome to the second part. And now we will have fun with discrete logarithms, obviously. Now we have already talked about discrete logarithms and we had some nice examples in the exercises, I hope. And okay, what is it? We are looking in Z star P, which is a residual field with respect to P, where only one number is forbidden and it's 0. Okay, and so this is P minus 1. And one can prove that in these fields we have a generator. And a generator which is a number, so if you look at all the powers, that we cover all elements. Now, how do we get a generator? That's something we show on the next slide. But if you look at examples, so for example, this is P is equal 7, and we start with 2, then 2 to the 0 is 1, so 2 to 1 is 2, 2 to the 2 is 4, and 2 to the 3 is unfortunately 1 again. So that's not a generator because there's some numbers missing here. Okay? But if we start with 3 and 3 is a generator, so we have 1, which is 3 to the power of 0. We have here 3 to the power of 1. Then we have 3 to the power of 2 is 9, which is 2, modulo 7. And we have 3 to the power of 3 to the power of 4. And then we have 3 to the power of 5. And now the interesting thing is that we have exactly 7 minus 1 possibilities going around. And we can also find the powers of 2 here, which are also here. Because here we have a cycle of size 3, and now we have a cycle of size 6. And in this cycle of size 6, we will find a cycle of size 3, where we actually jump over 2 possibilities. So we jump over 2 possibilities, because we start with 3 to the 2, then you have 3 to the 4, and then you have 3 to the 0. So we get all the factors of 7 minus 1. We could also have a cycle of length 2. For this, we would actually start here again. We jump to the other side. Okay. By overjumping 1, 2, 3 possibilities, and then we jump back. So we have a cycle of length 2 by jumping over 3 possibilities. So that means that from all these generators, we can look for other generators. So if you start here, so G of 1 will be a generator. G of 2 will be only a generator if P minus 1 is not divisible by 2. So it's probably not because it's too large. So G to the 3 could be a generator if P minus 1 is not divisible by 3, and so on. So basically all prime numbers, all numbers which are co-prime with phi of pi, G to the A, and if A, the G common divisor of A and phi of P, if this is 1, then this is a generator as well. Okay, so that's how we can get more generators. If we have one generator, we can immediately have other generators, which is a cool observation somehow. And so, observation, if G is a generator, then G to the I is a generator if a greatest common divisor of I and phi of pi is 1. So we are looking at set phi of pi star. That's the definition of a set. Now, how great is this set? Now, this set is the Euler function. So for a prime number P, there are exactly phi of P generators. That's not a typo. It's really phi of P. And that's how many generators do we get. Now, how large is it? Well, the answer is, of course, it depends. It could be very small. For example, if P minus 1 has a large prime number, Let's think of 23. Yeah? 23. Phi of 23 is, what is phi of 23? Okay, phi of 23 is 22. So what is phi of 22? So 22, I help you with factoring, is 2 times 11. Yeah. So we know that if you have factors, it is the factorization multiplied by 1 minus 1 over the prime number. So it actually is 10. So it is approximately 1/4 of 23 because we have a large prime number in 23. In general, you can prove that this number is larger than p minus 1 divided by 6 times the logarithm of p minus 1. Now, the logarithm of a logarithm is a very small number. So, in practice, you cannot distinguish that from a constant. And you also get a very good test this way, because you can test your prime number, whether you have a generator, is that you check whether you get a small cycle. So you could check for all prime factors of phi of pi divided by one of the prime factors of phi of pi, let's say q, whether your number g is equal to 1 modulo p. And if it's equal to 1, then you have one of these small circles, because you have to look at one of the divisors of if q divides phi of p. If this is the case, then you have found a small cycle. And so if you have a prime factorization of phi of pi, this algorithm gives you a very fast test to compute this. Unfortunately, prime factorization is hard. That's the whole idea of RSA. Yeah. But we can build prime numbers with large prime, where pi minus 1 has a big prime number. Yeah, so we can do this. So we can actually make them easy to be found. And one way is you start with maybe with q, and then q is prime number. When you compute q 2 times q plus 1, and you check whether this is a prime number. And if this is a prime number, we say, yes, found it. We don't know about how often these prime numbers occur, but in practice, we see that there are lots of prime numbers which have a structure that 2 times the prime number plus 1 gives another prime number, which is just some empiric result, but it's good enough for practice because it seems to work. Okay. Now, this cycle is easy to understand for small numbers, but larger ones, we have seen this interesting presentation with grayish squares. There's no structure that you can really find. And so there are schemes which build upon this discrete logarithm security. And first of all, you have to find what is a discrete logarithm. So assume that we have a prime number and we have a generator for this prime number. Then the exponential of x is just g to the x modulo p. So that's something you know, and we know that it repeats. And the logarithm will be that y such that x of y is equal to x. Of course, we only define the logarithm only for elements in Z star p. So we use x as element of Z star p in this case here. Otherwise, it does not exist. Now, for security, there is no efficient non-quantum algorithm known for this discrete logarithm. What I mean by non-quantum algorithm is, unfortunately, there is an efficient quantum algorithm which solves the discrete logarithm and factorizes numbers and can compute the order of a group. However, currently, this quantum algorithm needs some billion quantum bits. Billion quantum bits. And at the moment, we're selling computers with only 100 quantum bits and 4 are working. So between 100 and 1 billion is still a gap if you use a reasonable size of it. So we are secure at the moment. If quantum computers speed up, then this is not secure. And this also raises the question, what is a quantum secure algorithm, in the sense that is there some kind of cryptography where we don't have this efficient algorithm? Okay, but going back, assume for the moment that quantum computers are not very fast and don't have a lot of quantum bits. We're looking at El-Jamal cryptography. El-Jamal was an MIT student from Egypt who actually developed this scheme also around shortly later of RSA and so on were developed. And this has very nice properties which made it one of the most favorite crypto schemes for people doing research in this area. So what we do? First of all, we need a key. So the cool thing is that we can publish P. We are working modulo P, and P is something which everybody knows. And we also make sure that P minus 1 has a large prime factor, large prime number factorization. We need a generator G, which is easy if P minus 1 has a large prime factor, then we can check this very easily. But this is also public. It's not a secret. The secret is some random number x, which will be an exponent, and the public will be g to the x. So we use this. Now we are basically using that g to the x is a one-way function, and we cannot compute the logarithm. We don't know how to do that. But that's the setup only. Because the encryption is now strange compared to the things that we've seen before, because we take a message and produce 2 outputs instead of 1. Because we combine it with a random number. So all messages are automatically randomized. You remember that we had to introduce randomization into AES, we had to introduce it into RSA. Here it is part of the scheme. It's already built in. And what we do is we take this random number, and it must be secret, and it must be kept secret after encryption. So that's why we compute g to the k. And then we take the message and multiply it with a public key to the same power. So you're using this random key, this random message as a power of a public key and a secret key. And m is the relationship, is a factor which we multiply to y to the k. Okay, how can we decrypt it? So we get this pair of messages, and what we do is, so in the second place, we want to get this m out of this, so we take m, this first message, and divide it with the first part to the power of minus x. So let's see, we have m times y to the power of k, and divided by, and the first part is C1, which is g to the k, g to the k, and to the power of x. So that's the operation we're doing here. That's what we do here. Now, if we switch if you write this down, when this is m times y to the power of, so actually y is x to the power of, is g to the power of x, sorry. I have to redo this, undo this. No, can't do that. Can I move it? No. So I have m times g to the power of x, so that's y, to the power of k, divided by g to the k times x. And the only thing is now, the order is swapped, and we can exchange that, and so we get rid of that, and we have original message again. And that's the same as something we can see here. So what we have to do is we have to compute the inverse, but since we know the generator and the size of it, we can even compute the inverse using taken to the power of p minus 2. It also produces the inverse. So you can actually have this with a modular exponentiation. So for security, we still have a problem that it's vulnerable to chosen message attack. So don't encode message for somebody else, because you can do the same trick that we have seen in RSA. So but if you do not do that, then you can prove that encoding, decoding a message is as secure as computing a discrete logarithm, which should be hard. So a very nice property again is that for elliptic curves, we have semi-homomorphism. Okay, so we already have seen this for RSA. Let's look how it works on El-Jamal. So for this, we have to define what it means to multiply two code words, because now we take one message and produce a pair. And we see that multiplying a pair of code words is just multiplying the first component with the first component and the second component with the second component. And if you do that, and the first component times the first component gives this one, and the second component multiplies with the second component gives this one. So what we see is that we get the product of original messages, and we get a new R, which is the sum of R1 and R2 in the same structure that you used. So we can decode the same way. So we get a new valid message which has a product of two messages. So this is also a very interesting property that we will actually milk a lot. So we go there and we use El-Jamal, and this kind of methodology to get very complicated schemes. Now you could ask, so semi means half. What about full homomorphism? So full homomorphism is possible. First of all, it means that if you add two encrypted messages, then you have the encrypted of the sum, and if you multiply two encrypted messages, you have the encryption of a product. So this is possible to do with, for example, Parlier cryptosystems, which have a similar structure like RSA and El-Jamal, or you could use lattice-based cryptosystems to that, which have a completely different structure than the things that we have seen here. So for lattice-based cryptosystems, basically you have to introduce a completely new way of doing addition and multiplication, and this involves high-dimensional grids, where the security assumption is that it's very hard to represent this with small vectors. So this is a very interesting field, which has its cycles. So I know this scheme from, I think, the 90s. I saw it for the first time. And then they came up with some schemes, and then they suddenly were broken because they're not set up. And then after it in 2010, it has a revival and said, okay, you can use that in a way which is safe. So it's very important to use correct parameters. The cool thing is that it's supposed to be quantum secure, so that at the moment we don't have quantum algorithms which can work on this lattice-based cryptosystems. The bad news is that parameterization plays a huge role for this lattice-based cryptosystems. Now, if we look at El-Jamal schemes, so where is it here? El-Jamal encryption. Very often, you can it is shown that you can use El-Jamal or elliptic curves. So elliptic curves as an alternative to El-Jamal. And if you look at the elliptic curve encryption, it is very close to that. So again, it has elliptic curve encryption, has two code words, and has a similar structure. The only difference is that we're using plus and times instead of times and exponentiation. but with elliptic curve encryption is sometimes used just as a placeholder for that. So, what's the big deal about elliptic curve cryptography? And for this, we need some time to work through it. And we have to go back to the 16th century, basically, to understand what's going on and look at forgotten knowledge. So first thing is, why would you do elliptic curve cryptography to motivate you? Is you need smaller key size. So there are already some efficient algorithms or quasi-efficient algorithms which work on RSA and find something. And for elliptic curves, they say that 256 bits of elliptic curves is as secure as 3,000 bits of RSA, which is quite astonishing. The other thing is that the operating that we need are much easier. So we don't need, we still need something like iterative squaring, but it's also a very easy operation. So these elliptic curves have many applications. They're also used for integer factorization. An interesting fact, there are no ellipses. So they're not ellipses. They're just elliptic curves. So that's basically it comes from cubic equations. That is this thing. Cubic equation is the first thing you don't learn in school. Yeah. So who has seen cubic equation in school? Nobody. Did you ask for teacher for that? You have quadratic equation. How about cubic equation? Well, the teacher will assure you that quadratic equations have a lot of applications, but cubic equations don't. Because the first thing you don't learn in school. Which is a pity somehow. And you're deprived of this experience. But now you're at the university, you can learn about cubic equations, I think. Oh, yes. Okay. Is there a closed form solution for cubic equation? Is there a closed form for biquadratic equations or quartic equation? And why is a quadratic equation not using 4 in its name? Quadratic. It has 4 in its name. That's why we have to use biquadratic equations or quartic equations, because quadratic is also used by quadratic equation. Have you ever thought about that? I can give you an answer. How about quantic equations, which is degree 5? Let's start with quadratic equation. So this is something very, very old, not only in your school education, solving quadratic equations. The first solutions are known 2000 before Common Area become era, and I think people in India and some other places, they knew solutions to that, not only in your school. Why is it called quadratic equation? Do you have a clue? Yeah. Well, this is a quadrat, which is a square, which is a quadrat. Yeah. You know, in former days, you would not only formulate all your mathematics in Latin, but also you didn't have x squared plus bx plus c. So you were actually asking questions like, is the square of a length x and x plus a square plus a rectangle which has 3 here and x, and plus 5 extra dots, the same as a square which has x and 2x of that size. You would transform all kind of equation into a geometric setting. Because we know that the only basis that we have is Euclid and geometry. So everything came from geometry and arguing about the size of geometry. So that's why we talk about quadratic equation, because we always have this kind of a square inside it. And I think the word square also comes from quadratic. Okay, so far so easy. Now, if you look at the cubic equation, which has this general form, so the complete solution was found by Tartaglia and published by Cardano in 1540. 16th century. The interesting story is, in those days, you wouldn't publish results. So you actually, in order to prove that you're the smartest guy in town, you would send a letter to some other mathematician on the court of the place where you want to become mathematician and can ask, can you solve this riddle? I can. And they are sending letters to each other with small tasks or large tasks. And if I can solve it, then I'm a smarter ass, because the Duke was looking down and saying, okay, so obviously he has some letters from my mathematician and he tells me that my mathematician sucks at solving this equation, the solvents. So I take the other one, because he can solve much more complicated problems. That's the only way to prove that he knows something. Now, from a game theoretical point of view, this had led to the conclusion that mathematics was like magic, and you wouldn't publish your secret formulas, but you will only tell it to your scholars and say, here, you know, my son, I show you the solution to the cubic equation. Keep it a secret. Yeah, because otherwise we lose our position here. So they have these formulas and they read literature in order to find out. Now, Cardano has a very interesting life story. You have to look up his life once. I don't know why there's no movie about this. He invented a lot of things. Maybe you also know, if you look at a magnet in a cardanic. This is also from this. So you have a cardanic compass. So this is invented by him because it helps that you can find direction. But he also, that's the most important thing, he published a book about all these methods and was hated by his fellow mathematicians because he published all the secrets, like a magician publishing all the secrets of magic. And so he published the result of Tartaglia and, by the way, invented the root of -1, the imaginary number, in order to solve cubic equations. So it helps to have imaginary numbers to solve cubic equations. That's why we have them. And there's also a solution for this one, which was published in the same publication by Ferrari, together with the work of Cardano. And Ferrari was a scholar of Cardano. Okay, so we can solve that. There is a closed formula which fits on a piece of A4 paper. Like quadratic solutions, you can actually have a closed form with several cases. Now, for quintic equations, you can prove that there is no closed form. So we can solve everything up to here, but we cannot solve for quintic. That's the reason why you learn all the solutions for the quadratic, cubic, and the quartic equation in school. Yeah, you don't. You know, probably they think that 16th century mathematics is too complicated for you, I guess. If it's not written in Latin and describing some geometric forms, I guess. Okay, so much for this. But you can Google it or ask ChatGPT for it. So, okay. Now we want to work with cubic equations, and so we have to understand cubic equations. And so we start from scratch. Polynomials. So this is a polynomial of degree 0. That's just a constant. If a is large, then it goes up. If it's small, it goes down. So this is a line. Okay. Also important functions of this here. And these are the quadratic equations. So they all look the same, quadratic, because they always look like that. Yeah, or like that, which is just the inverse. And they are scaled and moved. So you can move them here and here, so you move them up and down and so on. In order to move, you would actually move by, let's say, x minus, give it name p. You move to the right by p steps. And if you move up, you have maybe some q. And if you want to scale it, then you have some factor a here. And so can you move it up, down? So you can scale it and make it larger by A. You move it to the right, you move it up and down, and so everything looks the same. It's just one way of parabola. That's why we talk about parabola, because they all look the same. And in school, you spend a lot of time in order to find out where it hits the strange line. And now we want to do the same for cubic equations. We don't want to solve a cubic equation, but we want to understand how these functions look like. Okay. Now the good news is you only have to think of 3 possibilities. So first of all, if you look at the cubic equation that we have here, the first thing is you divide by A. Now if A is not there, we have a quadratic equation and it's easy, but we divide by A and we get something like that. Okay. Now let's sort that out. So what can we do now? We can move this left and right. So if we move this by E steps to the right, then we have the function f of x minus e. And if you plug this in this formula, we get something like that. I hope I didn't make too many mistakes here. Okay, so you get a formula like that. Now, if we are clever and move it into the right so that this sphere is 0, we can move in such a way to the right that if you choose E is equal like the term B prime divided by 3, then we get rid of a quadratic term. So that means by moving right to a certain direction, we get rid of a quadratic term. So it doesn't seem to be important in the first place, this quadratic term, because we can remove it by moving to the right. And when we are looking in the so-called PQ form, that we have this cubic formula which doesn't have a square term. We are doing this in order to make things easier for the elliptic curves later on, so we can remove the quadratic term because it's just moved, and to the right is not important. Now, what we have is actually we have 2 terms. One is x to the 3rd power plus px plus q. What is plus q doing? What is plus q doing? Which is the interactive part of a lecture. Yeah, it just moves you up and down. So we moved left and right, so we can, now if you just want to learn the shape of a thing, we can ignore it, because whatever is the shape of this function, it is x to the 3rd power plus px moved to the right or up and down. So we just have to learn what is this doing. And there are only 3 cases. P is 0, P is negative, and P is positive. Okay, let's start with P is equal to 0. Yeah, that's a shape you know, x to the 3rd power. You can remember that. And the good thing is you can forget it because we don't need it. Okay, so that's something we don't need in the future. But for the moment, it's one case. Now if we look at this case, x to the 3rd power plus x, what happens is that we have this function and add an x to it. So we add this one. So we make it at every position, it gets steeper. So it looks like this function here. Okay? Goes up. Always positive. Now, this is somehow boring because it just looks like a non-straight line. And so let's look at the most interesting case, which is this one, x to the 3rd power minus x, because what we do is we have now a function which goes like that, and you go up at some point, then you go down, and then you go up again. So and these are the only 3 kinds, and everything else is just moved around, right, left, up, and down. So basically, after moving this to the correct place, we just have to look at the factor 3 in order to find out what's going on. So now we have good intuition what's going on. Now what we do as next is you compute the square root out of that. So an elliptic form in Weierstrass form is a curve which has this property. We have y to the square is equal to x to the 3rd power plus c2 times x squared plus c1 times x plus c0. So basically it means we compute the square root out of the cubic function. Okay. The first observation is this can be simplified by moving left and right into something like that. So we can move left and right and substitute y with something else. And we know that we have moved everything to the right. Okay. So, and here we have some example, but since we are living in the modern age, I would show this on a computer algebra system if it was installed on this computer, which isn't, because the faculty doesn't have enough money to do so. So let's look at, let's see, open with Willis Player. So I hope I wished I could use that program, which is it's fighting myself. Okay, what are you doing? Okay, this is also part of recording. Me struggling with Windows. Okay, so let's see if I can use the. No. Here, I have the controls here. Okay, so here you can see some functions. So here you can see y squared is equal to x to the third power plus 0x plus this one. So this is the function that we know. And what we do is we shift this. So if you just concentrate on the blue thing, you can see that this goes up and down. Okay, so far so easy. Now what I have computed the square root. Now here we have only values which are larger than 0. We have to concentrate, so this one. And so we compute the square root of this part, and we have a positive and a negative part. So this orange and green thing is the elliptic curve. And it looks like that. So it starts here, and then suddenly jumps here over this thing. So I think I have this in slow somehow. If I can read with small letters here. I have this here, okay. So you can see here that here it suddenly jumps over. So, and when it stops, because thank you for that. Can I get the controls that it doesn't stop? Here I have to press this button here, maybe. And maybe it remembers it. Yeah, okay, now it should go back and forth. Okay, so that's what, and you can see that it makes this strange curve here. But there are also other possibilities. Let's see what we do next is, let's see this case. And this is a case where we have a positive factor here. Now it's the same thing. Okay. So this is now an interesting case. So what we see is that here we have this. No, it's repeating the old things again. What is it doing? Actually, this is a mess. Okay. So now that's it's like old people using a computer here. It's really unfortunately I am old, so not even. And now it's repeating all the videos. I didn't tell you to do that. Huh? Maybe I start the Microsoft program, which will be much better. Okay, this is it has shadows. Okay, wonderful. I can press play it again. Okay, so that's the first one. Actually, I have this much better if Mathematica was installed on this computer. So I was thinking of a choreography. So this is don't go away. Stop it. Yeah, but where? Here, this turn repeat on. Okay, this might be working. Okay. Yeah, so okay. this is the control bar. No, it's a loudspeaker. Okay, now it's not so loud anymore. That's good. Oh, what is happening here? And hello? We're back. So probably I have to show you this on a computer when we have exercises. And maybe you're also invited to explore this function in order to see some interesting properties just by looking at it. I think the thing is I want to stop with this here. I made this list. Maybe we can close the lecture with that view. Now, what happens if I oh, interesting. Okay, what you can see here is that we have this function where we have x to the third power minus 2x plus something. And this is the cubic function that you see here. And if you take the square root, what happens is that you only see the values which are larger than 0. And now we see a curve which is separated. It could happen, but it does not need to happen because we have seen many curves. What we see is that we'll always have a part of this cubic function where it goes to infinity here and here, so it goes like that on this part. And the other thing is that if we cross here, if we cross the y-axis, it always goes perpendicular, except for one exception, which is if we have a function y squared is equal to x to the third power. So we always have these things. So it's always a very nice form. And that's why it gained some interest in the 19th century, that people were looking into, actually we're looking at all kind of polynomial functions, and it turned out that this has very interesting properties. That's why we could build a cryptography system out of it. The most important property is something you cannot really see, is that if you put a line here for this curve, it will always produce at most 3 intersections. Because if this will produce a new cubic equation, each cubic equation has at most 3 solutions. And taking that line through this curve gives us the real part of, so this, computing this line here through this curve will give us an operation which is called the star operation between P, Q, and R, because if we start with P and Q, we end up in R, and we use this operation to do cryptography. However, we don't use it for real numbers. We will do this in Elgamal field, where we don't have these nice fixtures anymore. But in order to understand how it works in Elgamal field, we have to understand how it works with real numbers. Yeah, so with this teaser, we run out of time and out of patience with all the operating system problems that we have today. And thank you for your attention today. Thank you.